Got another exam walkthrough from Moments. This is going to be 2025 June, question number 2 and question number 19. So this is the question. You can try it yourself. Here's the next part of this question. And for the mark scheme, you can go to the end of the video. So it's rare that we see MCQs from Moments, but this one isn't that tough. So it says a seesaw is a uniform beam that balances on a support. The beam can rotate around the top of the support. Two children of equal weight, and then the uniform also is important, uniform beam, sit on a seesaw at equal distances from the support as shown. Which row of the table describes the resultant force and the resultant moment on the beam? So we have two children who have the same weight. So I'm going to say W1 and W2, and W1 is equals to W2. And then they're at equal distances. So I can just say that both the distances will be D. And you can see that the moment here will be anti-clockwise and the moment here will be clockwise. And once I find both the moments, so anti-clockwise moment will be equals to W1 times D, and the clockwise moment will be W2 times D. And both of the values will actually be the same thing. So our resultant moment will be equals to 0. So it's going to be either A or it's either going to be C. Now we should talk about the resultant forces. So first I'm going to label all the forces that are there. So here we have all the forces. So we have the weight of the child 1, weight of child 2, weight of the beam, and the reaction force. Now here what's going to happen is that the reaction force is going to be equals to the weight of the beam plus W2 plus W1. So hence our resultant force will be equal to 0 because upward forces and downward forces are balanced. So resultant force will be 0, hence our answer will be A. So I hope that's clear. Now let's move to our question number 19. Now you can read the question. If I go on to read this question, it's going to be a bit boring. So I'm going to straight up answer the question A. So it says when the rail is in equilibrium, the principle of moments applies. State what is meant by the principle of moments. So that's going to be in equilibrium, the resultant moment is equals to 0. Okay, so we have the next part, which is going to be BI and BII. They're a bit more difficult, but I'll try my best to explain it as clear as possible. So it says after taking the bike off the rack, the student lifts the rail back to its original position. The uniform rail has a length of... So one of the things I spot instantly here is that the rail is uniform. That's a very important point. That means the weight acts from the geometric center. So the uniform rail has a length of 1.4 meters and a weight of 95 newtons. The student applies a force F to the handle perpendicular to the rail. So this is the force F right over here. And then it says the piston applies a force of 160 newton to the rail. And then it shows the diagram of that, and it tells us determine the minimum value of F needed to lift the end of the rail off the ground. Okay. So the minimum value of F would be when anti-clockwise moment is equals to clockwise moment. That would be the minimum value of the force. So all we have to do here is we have to find the clockwise and the anti-clockwise moments, and we have to equate them. So to find the anti-clockwise moment and equal to the clockwise moment and do all of that, we have to first make components of the forces. So I can see that I can make two components here. It's going to be 160 sine 18. And then I have 160 cos 18. And I can see that the force that forms the perpendicular distance is going to be 160 sine 18. So there will be a moment due to this force. There will be no moment due to this component of the force. So we're going to have a anti-clockwise moment. So 160 sine 18 times, and the perpendicular distance is given 0.37. Plus, we have the force F, which is also having a anti-clockwise moment. and then we're going to have the perpendicular distance to the force. We can see that they're perpendicular to each other, so that's a thumbs up right there. And then I put 1.4 is equals to the clockwise, which is going to be this force right over here, 95. But the 95 Newton force is not perpendicular to the distance. This distance right over here is going to be 1.4 divided by 2, which is going to be 0.7. Because it's a uniform rail, so the weight acts directly at the center. So this is going to be 0.7, 0.7, 1.4. Let me just erase all the stuff here. So yeah, so this is going to be 0.7 meters. This is going to be 1.4 meters, 160 sine 18. And now what we have is we have to make components of this 95 Newton force to find the component that is perpendicular to the distance. Okay? That is perpendicular to the distance. They both need to form a 90-degree angle, the force and the distance from the pivot. So what I can do here is I can see this is going to be 90, this is going to be 48. And if you do 90 here, plus 42, plus 48, that gives you 180 degrees. You can also do something you do with the inclined plane. If you remember the inclined plane chapter, inclined plane, then you can take this to be as 42 degrees as well. That's totally fine. You can do it either way. Okay. And this is going to be 95 sine 48. And this right here is going to be 95 cos 48. There will be no moment due to 95 cos 48. There will be a moment due to 95 sine 48. So this moment is going to be clockwise. So we're going to plug in the value there. 95 sine 42 times the distance that's perpendicular to the force, 0.7 meters. And then we solve to get the value of F. So we get an answer as 22.2 newtons of the value of force. Now, after you solve it, you get this. Now, this is the minimum value, which means F can be greater than or equals to 22.2 newtons. So if you apply a greater force than 22.2 newtons, that's good because we want to lift the rail off the ground. So we want a higher force than this, that's totally fine. We can apply something like 25 newtons. That's gonna be enough to lift the rail off the ground. We're gonna have a greater anti-clockwise moment and your rail will go off the ground. The next part tells us the student could have lifted the rail by applying a vertical force upwards to the handle. The force needed to lift the rail is different when the force is vertical compared to when the force is perpendicular to the rail. Explain how the minimum vertical force needed is different. You do not need to include any further calculations. So I'm going to show you a diagram and we'll understand it and then we'll answer the question. So here I have a diagram. Now from here we can understand a bit further on what's going on. So first thing let's understand is from the previous question. The moment due to F plus, now the moment due to 160, I think it was 160 sine 18 is equals to moment due to the force that was 95, the component that was 95 sine 18, not sine 18, it was sine 48, So all of these moments must remain the same. Okay, you see this moment and this moment, they will not change. Okay, this moment should also not change so that we are in equilibrium. Okay, that's an important point. So our moment due to force F must remain the same. So moment due to force F must remain the same that it was. Okay. Remember, we're talking about the minimum value of F, at the minimum value of F. Okay. Now, we're looking at two situations that the question tells us. One, if the force F is perpendicular, then it's going to be F times 1.4 is equals to the moment. I'm going to write M and then I'm going to write F right there. And then in the other case, the question tells us that if the force is vertically upwards, which means if the force is vertically upwards like this, it's just straight line along the y-axis. At that point, what would happen is your force F would form an angle now. It would no longer be perpendicular. So we would have to treat it the same way we treated the other two forces of 160 Newton and 95 Newton. We have to make components at that point. So we will make two components, F sine theta and F cos theta. F cos theta, we don't care about it because it doesn't cause any moment. F sine theta, on the other hand, is going to be perpendicular to the 1.4 meter distance. So hence the moment will be F sine theta times 1.4 is equals to mf. Now, we said already that the moment due to F must remain the same. Now, if we see this two equations that we have F times 1.4 and F sine theta times 1.4. Obviously, those are different values because you have sine theta in one of them. And in this case, what's going to happen is we're going to be changing the value of F. Okay? We're going to be changing the value of F so that F sine theta becomes equals to the F that was there before. And remember, we found the minimum value of F. The minimum value of F is 22.2 newtons. So we know F sine theta, on the other hand, maybe it could be lower than that. It's definitely going to be lower than 22.2 newtons. Okay, so it's going to be F sine theta, let's just write it like this, is going to be less than 22.2 newtons. Okay, so 22.2 newtons is going to be less than that. Now, what we need to do is we need to increase the value of this to make sure that F sine theta becomes equal to 22.2 newtons. And what we need to do here specifically is we can't increase the sine theta because we want to make sure that our force is vertical. So what we can do here instead is we can increase the value of F so that F sine theta will increase and become equals to 22.2 newtons. Okay, so if you remember the F value, minimum F was 22.2 and then 22.2 sine theta. So what I can do is I can increase this 22.2 to become 25 sine theta. Okay, and that's going to increase the value of the F sine theta just for the example. Okay, just for example's sake. Okay, so that's what we need to do. So the value of the minimum force would need to increase. That's basically the answer. So hope you get that. I explained it in detail, telling every little thing so you understand the concept. So here's going to be your answer. The moment due to force about the pivot must remain the same. The distance from the pivot remains at 1.4 meters, so it's the same. The component perpendicular to the rail, which was F sine theta if you remember, must be equals to the minimum value of F, 22 0.2 newtons. So the force F that we need would be greater when the force is applied vertically. Okay, so that's going to be the answer to this question. Alright, so hope that's clear. I'm going to show you the mark scheme and then we'll end the video.